Hello. Today we're going to be talking about maximum power transfer. So in many applications, circuits are designed to power a load, which makes sense. If we want to run a motor or lights or whatever, we would design a circuit to power this load. So among these applications, there are many cases where we wish to maximize the power transferred to the load. And unlike an ideal source, internal resistance will restrict the conditions where maximum power is transferred. So we talk about an ideal source. The way we normally think of a battery or a power source is where it only produces voltage or it only produces current. But in a real condition, this is not the case. It will have internal resistances and all that kind of stuff built into it. Whereas when we work with an ideal source, it does not have internal resistance, but now we're looking at adding an internal resistance to that. Okay. So maximum power transfer, we can use the Thevenin equivalent circuit for finding the maximum power in a linear circuit. We will assume that the load resistance can be varied. So just like a power outlet at your home, you can plug in any load you want, so that will be varied, and we want to work out the Thevenin equivalent. Looking at the equivalent circuit with load included, the power transferred is this. So P is power in watt. We have the Thevenin voltage equivalent, resistor Thevenin equivalent, and the load resistor, that all squared times the resistance of L. So that is basically the power equation. So this you work out actually current, and current squared times resistance gives you power. So that is the power that your load has available to it. So for a given circuit, voltage Thevenin and resistance Thevenin are fixed. So if you have a battery, the Thevenin voltage and the Thevenin resistance will be fixed. It will have a fixed internal resistance and such. So by varying the load resistance, the power delivered to the load varies as shown. So here you can see as the load approaches 0 and infinity, this way, the power transferred goes to 0. So the power, this axis, goes to 0. So why is this important? So let's say you have, this will become more important when we talk about power electronics later on, when you're powering a large amount of big motors or refrigeration systems, that kind of stuff. When we go into apparent power, real power, a lot of power can be lost, like this side of the curve and this side of the curve. So we would like to power our devices right at the maximum power transferred, because the power on either side of this, that kind of, if we're, let's say our Thevenin resistance is here, or our load is here, then we lose that amount of power. The same on this side. If we have our load resistance here, we will lose this amount of power. But if the Thevenin resistance and the load resistance are the same, that is when maximum power is transferred. So this implies that these two are the same. So the Thevenin resistance minus load resistance equals 0. So this then implies we said the load resistance is equal to the Thevenin resistance for maximum power transfer. So from that we come to this equation. So for maximum power transferred, we use this equation. Equation applies only when the load resistance is equal to Thevenin resistance. Okay. So now we come to a little example for make clear what we mean. So find the value of RL. So this is a unknown resistance. We must find the value of RL to ensure maximum power transfer in the circuit. Okay, so we work out RL for maximum power transfer. So to do that, we work out the venom resistance. So we take out all the power sources, replace them, and then we find out the venom resistance and the Venn voltage across the terminals A and B, where our load resistor is. So here we get the venom resistance in series, and these two, which is then in parallel with these two. So to get venom voltage, we add back in the power sources. We do our mesh analysis with the loops. We get our two equations, minus 12 because we had the minus again, and 6, 12, 18, and then minus 12. So here we work out I2 equals to minus 2 amps, because this is I2 and we have a current source there. So we can work out everything from here. Solving for I1, we get I1 equals minus 2 over 3. Applying KVL around the outer loop, we get the voltage, the venom voltage across A and B, which is 22. For maximum power transfer, RL must be equal to R, the venom, which is 9 ohms. And then we use those values we calculated in our maximum power transfer equation. So source modeling, take the venom circuit with the load resistor, the internal resistor and the load act as a voltage divider. The lower the load resistance, the more voltage drop occurs at. So what we're doing with source modeling is we are modeling a non-ideal battery, like a real battery. If we really want to know what is going to happen with our circuit once we use it, you will model your battery with its equivalent resistors. So this means that as the load resistance increases, the voltage source comes closer to operating like the ideal source. Similarly, with a realistic current source, the internal resistor in parallel with the ideal source acts as a siphon to siphon with the current that would otherwise go to the load. So this just means that in a real battery, as the internal resistance with the ideal source goes higher, it siphons away the current. So that's what happened in the real situation, and that's why we want to do modeling. So here the load and the internal resistor act as a current divider. So here it siphons away the current here, and this is the current going to the load. From that perspective, the lower the load resistance, the more current passes through it. Thus, lower load resistance leads to behavior close to ideal source. Okay, so if the load resistance is lower, it reacts more like the ideal source. Because if the load resistance is lower, there will be more current flowing through it. Less current will branch through the bigger resistance there if this one is a lot lower. So although the ohm meter, so now we come to another application. So the first application was source modeling. Now we come to resistance measurement. So although the ohm meter is the most common method for measuring resistance, there's a more accurate method. And this is called the Wheatstone bridge. It's a very important circuit that we will be, well, that is used in a lot of electrical engineering work. Is what we call the Wheatstone bridge. It's based on the principle of a voltage divider. So here's a circuit. You have a voltage source, one resistor, variable resistor, third resistor, and an unknown resistor, and then a galvanometer. So using 3 known resistors and a galvanometer, what is a galvanometer? So a galvanometer is a mechanical device which measures the direction and the magnitude of current. So if we insert our galvanometer there, it'll tell us which way the current is flowing and how many amps are flowing through it. And then our unknown resistor, which we are testing. So under resistor is placed position Rx, the variables R2 is adjusted until the galvanometer shows 0 current. Now why is that? We'll follow that. So at this point the bridges are balanced and the voltages from the two dividers are equal. So looking back at the circuit, so our voltage here, R1, variable R2, R3 and Rx, and our galvanometer here. So when we adjust this resistance here, you'll see the galvanometer, the direction of current might change and the magnitude will definitely change until you adjust it in such a way as this becomes 0, which means there's 0 flow of current from this point through to that point. And why would there be 0 current flowing through here? Well, as we stated previously, this means that this bridge here is the same voltage as this bridge here, which means these two are in parallel, same voltage as here. Current only flows from a positive to a negative potential, or in a potential difference. If there's a potential difference between 2 points, then current will flow. So we're adjusting this resistor until this branch's voltage is equal to this branch's voltage. Then there is no current flowing. Okay. So once we've done that, we can use our equations for this, just a rearranged equation to work out the parallel resistor's value, and we can work out Rx, because you have R1, R2, and R3, because R2 I think is the variable resistor, so we measure that and then we know exactly what Rx is. So the key to the higher actually lies in the fact that any slight difference in voltage will lead to current flow. So if there's only a slight change in the voltage of the one branch to the other branch, there will be current flow. Then you have to adjust your resistor, adjust the resistor until there's no difference between the two bridges, and then you can use this equation to work it out. This just shows how when current will flow if there's the slightest amount of difference. So with a bridge, less the under resistor is reduced to a Thevenin equivalent. Okay, and that is it. I hope you enjoyed this video, and you can watch it over and over again and let me know if there are any questions. All right, goodbye.